Hi everyone, so in this video I want us to go through one of the methods in which we can use Google Sheets to solve discrete dynamical systems. So the discrete dynamical system I want us to focus on is this one I've written over here. It's a exponential growth model where the next iteration is equal to the previous value plus some parameter k times the previous value. And of course we're given things like the parameter value and the initial value to start the iterations off from. So we're going to use this recipe to find other iterations, as many as we want using Google Sheets. So let's actually take this equation and put it below. It's like a little stuff came for the ride. But all right, in this problem, just to start us off, I want to define the values of k. Let's just make k equal to say 0.25. And let's start our initial value, or set our initial value at say 10. So these two items we're always going to be given before we can start iterating, because we need to know what the parameters are, what their numerical values are, to actually get the next iteration value, as well as we need to know where the iterations start. So we need that initial value p sub 0 to get p1, and then from p1 we can get p2, from p2, p3, and so on. So in Google Sheets, I'm going to show you one method to do this, and this is the method in which we're going to assign or define basically a variable name or parameter name to a specific grid cell. So we're able to call, say, the value of k anywhere we want in the Google Sheet. So just like I said in class earlier, the way in which I like doing this is basically just starting off by making a list of parameters. Well, in this model, we only have one, and that parameter is k. As well as we can make a list of initial values. In this particular model, we only have one equation, so we only need one initial value. And we only have that equation as first order, which means to get to the next iteration, we only need to know the information about the very previous one before that. So I'm just going to set next to k and next to p0 those numbers that we outlined here. So 0.25 and 10. At this junction, if we tried writing, say, equals k anywhere to use that value of k, it doesn't really know what we're talking about. In fact, it thinks we're talking about kurtosis of a data set. So what we want is actually to be able to call the value of k from any grid cell we want in this spreadsheet. So in order to do this, if you just want to click on that value of k that we have, 0.25, we can go up to data. And once we're in data, we want to select the thing that says named ranges. This is going to allow us to assign a string declaration or a string to a particular grid cell. In this case, we're going to click add a range. We want that to be called k because that's our parameter. And we want to assign k the value that is in grid cell B6. So once we have that set up, we can click done. And now anywhere in our spreadsheet, we can just use that value of k. We can write equals k. We could write equals 2 times k plus k squared. And it's still going to figure out all of that arithmetic for us because k is now a defined variable. The other subtle thing I want to just mention is these k and p sub 0 values we wrote in the A column are just to help us stay organized and know what that value on the right in the B column is going to refer to. So let's name that p sub 0 value as well. Since we still have that named range thing open, we could go click add a range. But if you've closed that dialog box, just as a quick reminder, click on data at the top, named ranges, and it'll bring us back to that named range. So from here, we want to call this p underscore 0 for initial value. And the underscores will be helpful for us to stay track of variables. Because for example, we're not going to be able to define variables, say p1, p2, because there's going to be a column called p and a row called 1, 2, or 3. So the underscores will help us stay track of parameters or a particular grid cell in the spreadsheet normally. So once we're highlighted on the value that we want to define p underscore 02, we can click done. Now we get to play with that value of p underscore 0 anywhere we want in this as well. Oops. All right, so at this point, we have defined our parameters. We've defined an initial value. To give you a sense of this model has one parameter, a model could have 2, 3, 4, 5, many, many parameters. So we go through the same process for the amount of parameters that we have. I'm just going to click or close this named range dialog box since we're done using that. And the next things that we need to do is basically start creating our list of what the iteration number is, or the index, say n, our nth value of that discrete dynamical system, p sub n, and we can make another column to designate the next iteration value to that. And I just want to show you a few of the very special features that Google Sheets has that makes it a very, very useful tool for us. So under the D column, we want to start writing basically the iteration numbers we're going to use. We were told that the initial value is defined at the 0th index for n. So n equals 0, and then we're going to iterate to 1, 2, 3, and beyond. So let's start off by typing 0. If you click enter in Google Sheets, it'll bring you to the row right under it. So we can write 1, 2, 3, 4, 5. Now, if we wanted to go all the way to say 100, this would be a pretty annoying process of just clicking enter, clicking the next integer, clicking enter, clicking the next integer. But luckily for us, Google Sheets has this very nice pattern recognition feature, where if we highlight a bunch of cells and then hover over to the bottom right corner of those highlighted cells, Google Sheets, or Microsoft Excel for that matter, is going to do its best job to pick up on a pattern from one of those cells to the other. So if we just click and drag down now, it's going to do its best job to pick out what pattern we just had and just continue that pattern on. So this will become very useful for us because we don't want to have to keep writing the same equations over and over, or defining grid cells over and over in the same way. We can be very lazy mathematicians, mathematical biologists, or biologists, and just go through this process of clicking and dragging. So under E, we want this first value for the nth iteration to be equal to p sub 0, our initial value. So we can just write this as equals, and then p underscore 0. And you'll notice that that item in B10, where we defined that initial value as p underscore 0, highlights. And if we click enter, we should see a 10 pop up there. Now, what I want to draw our attention to is this sort of diagonalization that's going to happen between the value of p0, noting that the next value that we really want here is like p1. I'm just writing this so we know, hey, p0 is to the left, p1 is to the right of that. But what we'll have, if I just write this out on the screen next door, is we'll have a column that have all of our index or indices. The next column over will correspond to the nth iteration value. So like P0, P1, P2, P3, and so on. The next column beyond that will be the n plus first column. In other words, it'll be the next iteration. So at this first row, where we have n equals 0, the last item we'll have in that row is P1. When n equals 1, the last item we'll have in that row, or the next iteration, will take on the value P2. And the pattern I want you to recognize in the way that we're structuring these columns is that if we have P1 in the top row, we see that P1 show up again, sorted to the left and downwards, in the column to the left of it, but one row down. And we'll notice that same pattern emerge for all of the P values. The next iteration will show up as the following row as the nth iteration. So what this is going to allow us to do is basically assign all of these grid cells ahead of time. So for example, in grid cell E6, this we know to be taking on the value of P1. Now, if we look at the value of P1 though, it's equal to that upper diagonal grid cell. So we can say this is equal to, now in the F column, the value of F5 for me. And you'll notice that the values highlight. We can click enter. Lo and behold, nothing happened because there's nothing in that grid cell F5. But if we were to put, say, 33 in there, we would see a 33 then pop up kind of on that other associated diagonal grid cell. So I'm just going to get rid of that value in F for right now. But we can do this diagonalization argument as many times as we want. In fact, we only do it one more time and then we'll hope that Google Sheets will pick up on the pattern for us. So in grid cell E7, or 2 below that initial value, let's say this is equal to, now the next value for P2, if you look on the left-hand side, is that upper right box as well. So we can say this is equal to the value of F6, the upper diagonal box. Clicking enter, nothing showing up because we don't have anything in that F column for F6. But we can highlight those 2 values we just assigned as those diagonal elements. And once we do that, we can click or highlight or hover over the bottom right-hand side, click and drag downwards, and we've continued that pattern for all of the solution iterations we care about. So for example, if I click next to this 13 in row E18, we want this to equal the value of F17, which you can see it actually does take on. So the next thing for us to actually do is just type in our recipe for getting to the next iteration. So we're going to go back over to the value or the box F5 right next to our initial value from E5. And we just need to type in the recipe that we have at our disposal right now. So our recipe is the next iteration is equal to the previous iteration plus that parameter K times the previous iteration. So we just need to do this operation. So we can say this is equal to the previous iteration, the grid cell directly to the left, plus K, which we've assigned that value in B6 as 0.25, times, well, that previous iteration, which is that grid cell directly to the left. So we have E5 plus K times E5. And we can click enter. And lo and behold, we get the next iteration value, as well as we get that additional diagonal grid cell filled in automatically. Now, what's nice is we can again use that Google Sheets pattern recognition. It's going to do its best job just by recognizing that one equation we have. So if we go to that equation that we've written in F5, go to the bottom right-hand corner, click and drag, it'll give us the remainder solution values. And the last thing I'm going to do in this video is just help us plot this data very quickly. So I'm going to extend the size of this Google Sheets screen just to show us how to make some charts in Google Sheets. So if you click on data, actually that's not where we want to go. We want to go over to insert, whoopsie, and we want to click on chart. It'll take my computer a few moments. Hopefully it doesn't go crazy. All right, and it seems to have tried to automatically plot some stuff for us. I'll resize this to see if it's the best we can. And now it may have defaulted to a pie chart, a scatter plot, a bar graph. From what I've seen, Google Sheets likes defaulting to whatever it wants. We want the chart type, so if you double click or right click and go to edit, you can go under setup on the chart editor, click on line chart or the chart type, and we're just going to scroll down to scatter plot or a scatter chart for that matter. So if you click on that, you'll see individual points. Now, you might get lucky like here. It looks like, hey, it's actually plotting our solutions for us. If it didn't plot anything or it's plotting what looks like garbage, it's probably plotting the wrong thing. So we want to remove anything that's previous under x-axis or under series. So we need to actually add the data we want for this chart. So if you click on Add X-axes, you might see to the right, select a data range. We want to click on that. This is going to allow us to select a range just by highlighting what values we want to use as the independent variable or the horizontal values or horizontal axes. And we want this to be the n values. So we can select 0 through 15 in my case and just click OK. Nothing happened. Well, because we didn't tell it any of the dependent variables yet. So we can scroll down to series, click on add series, and again, we want to select a data range. And the data we want to add here under series would be whatever our y values are or what the dependent variables are in our case, those associated with the vertical axes. So if you click on select data range, we want to highlight the iteration values for p sub n. So under the E column, I'll highlight the 10 to the 284 and change, the last value of the solution we have, and click OK. And you can see our solution as n increases. Now there's some funky titles and stuff happening here. So if you wanted, you could, change the chart titles. You can add axes labels for the vertical, for the horizontal axes, and all of that jazz. But I hope that at this point, this video has helped you kind of solve a discrete dynamical system using this method in which we explicitly define each of the variables. And the last thing I want to show us is the powerful technique of this method is we can hover over or mosey on over to the column B, and we could change these k values. Say instead of k 0.25, we have 0.99, and it'll update our entire solution for us automatically. So we essentially now have these knobs that we can turn just by changing these parameter values. Similarly, you could change the initial values and see how the solution changes as you modify some of these parameters. Check out the next video as we discuss how to do this, but without defining explicit variable names or named ranges for k and p0. We're going to do everything just using columns.